Hello everyone. Through this video, we are going to discuss about the questions of exercise 1.1 in the chapter of real numbers. So here is the first question. Use Euclid's division algorithm to find HCF of 135 and 225. Roman 2, what is said here, 196 and 38220. Then number 3, 867 and 255. Let us start with the first part, 135 and 225. What is Euclid's division algorithm? We had already gone through in the previous video in the preliminary informations of this exercise. So what actually it says, if A and B are any two numbers given to us, positive numbers given to us, where A is greater than B, then there exist two integers Q and R such that A is equal to BQ plus R, such that 0 less than equal to R less than B. Here in this case, we have to remember one thing, that if A is greater than B, if A is greater than B, then B can divide A. There will be some quotient and some remainder. This remainder should always be following this condition. That means remainder should always be greater than or equal to 0, but it must be less than the divisor, that means B. Let us understand this through an example. Suppose 5 and 3 are two numbers given to us. We have to find out its HCF, HCF of 5 and 3. So of course, when we follow Euclid's division algorithm, we have to divide 5 by 3. When we divide 5 by 3, we get 3 1 ja 3. What is the remainder? 2 is the remainder. So it is very clear from here that this remainder 2 is less than 3. So no further division is possible here. When we apply the steps of division algorithm, we shall be getting 5 is equal to 3 into 1 plus 2. So this is the division algorithm, and Euclid's division algorithm is just a restatement of the division algorithm which we have been learning since the lower classes. So we are going to follow those steps only. What I said just now, what explanation I had given just now, this first expression follows that particular rule. That means here in this case 225 is bigger than 135. So of course 225 is divisible by 135. While dividing 225 by 135, let's check what we get as quotient. Of course it is 1. 135, 1 ja 135. So the remainder comes as 90. While we subtract, we get the remainder as 90, which is a non-zero term. Now, following the division algorithm, we can write this in this way. 225 is equal to 135 into 1 plus 90. Here in this case 1 is the quotient and 90 is the remainder. So we find that 90 is a non-zero remainder. One thing we should remember here, that to get HCF following Euclid's division algorithm, it is very essential to get a step where the remainder comes as 0. So in the first step, as we got a non-zero remainder, that is 90, we have to repeat the same steps once again, in which 135, the divisor of step 1 becomes the dividend in step 2. Again, the remainder, the non-zero remainder of the first step becomes the divisor in the second step. So in this second step, 135 is taking the place of the dividend. Then 90, I mean the remainder of the previous step, is taking the place of the divisor. And then after, we are going to repeat the same process as we did earlier in the first step. So of course we have to divide 135 by 90. While dividing 135 by 90, we are getting the quotient as 1, and the result that we are going to put in this place will be 90, of course. And after subtraction, we are getting back the result 45. So 45 is the value of the remainder here. So in this second step also, we found that 45 is the remainder, which is a non-zero term. I mean a non-zero number. So our intention is to get a step where the remainder comes as 0. Since we did not get the remainder as 0 in the second step also, that is why we have to move on to the third step using this 90 as the dividend. I mean, in the second step, 90 was the divisor. So to carry on the third step, I mean to continue with the third step, we have to make this 90 the dividend in the third step, while this non-zero remainder will become the divisor in this third step. Now let us check what do we get. In this third step, of course we have to divide 90 by 45. While dividing 90 by 45, we got 45 2 ja 90 and got a 0 remainder. So when we get a remainder as 0, this will be considered as the final step using Euclid's division algorithm. Now the special thing here is what? The divisor of this last step, I mean final step, where we are getting a 0 remainder, will be acting as the HCF here. So the required HCF in this case is HCF of 225 and 135 is 45, and this is the required answer. Moving on to the next question of question number 1. Here we find two numbers 196 and 38220. In these two numbers, we find that 38220 is greater than 196. So like the previous question, here also we have to apply Euclid's division algorithm. Applying Euclid's division algorithm, the first thing that we have to do here is what? We have to divide the bigger number by the smaller one to get some quotient and some remainder. So let us check here. When we divide 38220 by the term 196, we get that the quotient comes as 195 only, that is already derived here, 195, and the result comes at 38220, in which we got 0 remainder. So here in this case, the bigger term is taking the place of the dividend, while the smaller number is taking the place of the divisor. Then when we perform the division, we got this 195 as the quotient, while 0 comes as the remainder. Since just in one step we got all the result here, I mean we have already got a 0 remainder, therefore 196, I mean the divisor of this step where we got 0 as a remainder, will be acting as the HCF. Therefore the required HCF of 38220 in 196 is 196, and this is the answer of the second question. So here is the third question on the question number 1. So here we find what? Two numbers, sorry, 867 and 255. In these two numbers, 867 is bigger than 255. Like the previous two questions, again we are going to proceed with Euclid's division algorithm here. And what do we have to do here? The bigger number should be divided by the smaller one. So when we divide 867 by 255, first of all, we get the quotient as 3. Let us check what result do we get. 3 5 are 15, 1 left. Then 3 5 are 15 again, plus 1 6. Then again 1 left. 3 2 are 6 plus 1 7. So on subtraction we got result 102, and that is what we have to put here. 867 will be taking the place of the dividend, while 255 will be acting as the divisor. After that, when we perform the division, we got 3 as the quotient and 102 as a remainder. To get HCF, of course, we have to derive a step where the remainder comes as 0. In this case, as this is a non-zero remainder, we have to continue with the same steps. So again, in the next step, in the second step, 255, the divisor of the first step will be taking the place of the dividend in the second step. Again, the non-zero remainder will be taking the place of the divisor in the second step. So let us check what do we get when we divide 255. Of course, we have to perform division once again. We have to divide 255 by 102. While dividing 255 by 102, we got 102 into 2, it is 204. Then what remainder comes here? 51. We got the remainder as 51. So we can place these terms in this particular rule. Following this rule means 255 is taking the place of the dividend, while 102 will take the place of divisor. On a performing division, we got 2 as the quotient and 51x as the remainder. So here again we got 51 as a non-zero remainder, and that is why we have to continue the step once again, in which the divisor of the previous step will be taking the place of the dividend, while the non-zero remainder will be taking the place of the divisor in the third step. And after that, let's see what we get. So again we have to perform division. 102 should be divided by 51. So 102 when divided by 51, let us see what do we get. 51 2 ja, it is 102, and here we got our required remainder, the remainder 0. So this is the step where we got 0 remainder, as a result of which 51, the divisor, will be performing the role of HCF. So here is the HCF, it is 51. So this is the answer of the third question under question number 1. Now moving on to question number 2. So what the question says, let us see. Show that any positive odd integer is of the form 6q plus 1, 6q plus 3, then 6q plus 5, where q is some integer. So we have to show that any positive odd integer, the number should be positive, the integer should be a positive integer, and it should be an odd integer. What does the term odd mean? Actually, the integer should not be divisible by 2. In other words, 2 should not come as a factor in case of when we do factorization of that integer. It should be of the form 6q plus 1, 6q plus 3 and 6q plus 5, q being any integer. Now, how to solve this? So, in this case, we consider any positive integer a. Suppose a is any positive integer, and along with this we consider another integer b, in which actually here in this case certain things can be observed. 6q plus 1, 6q plus 3, 6q plus 5, these are certain formats. If I consider say any integer, this odd integer, let us consider the integer to be a. Let us consider the integer to be a such that it can take the form 6q plus any number r. Actually, in this question, the value 6q, 6q, 6q remains constant. We can observe changes in the later part of these expressions. I mean 1, 3, 5. These are the changes we can observe here. That is why it is better to consider the number, I mean the integer, as which actually whether it is odd or even, that is not yet decided. We have just considered the integer to be a. Whether it is positive, I mean of course it has to be positive. Whether it is odd or even, that will be decided later on while solving the sum. Okay, so when we consider the integer to be a, we have decided to consider another integer b. Say a and b are two integers. Now, as we can observe here, these numbers 6q plus 1, 6q plus 3 and 6q plus 5, this 6q as constant value. That is why we consider, I mean we can relate a and b in this way. A plus bq plus r. Now if I replace b by 6, then a can be of the form 6q plus r. So 6q will be constant everywhere, just changes will be there in the term r. How this term r will be getting changed according to values, let us check here. So a is any positive integer where b is 6. I mean a and b are two integers where a is any positive integer and b is value of b is 6. Then by Euclid's division lemma, as we know Euclid's division lemma as a statement in which states that when a and b are any two non-zero integers, non-zero positive integers, then there exists integers q and r such that a is equal to bq plus r such that 0 less than equal to r less than b. So this is actually Euclid's division lemma. Now that is what is said here. By Euclid's division lemma we get a is equal to bq plus r. Then there exists integers q and r such that 0 less than equal to r less than b. Actually a is the dividend here, b is the divisor, q is taking the place of quotient while r is the remainder. While solving the previous questions already we have noticed one thing, that the divisor is always bigger than the remainder. Therefore b is bigger than r and the remainder should either be equal to 0 or should be greater than 0. Or should be greater than 0. So that is what we have observed here. Now when we replace b by 6, we got a is equal to 6q plus r for 0 less than equal to r less than 6. That means this b will be getting replaced by 6. So values of the remainder will be in between 0 and 6. But 0, it can be somewhere equal to 0 also. That means the remainder is either greater than or equal to 0, but it has to be less than 6. Therefore, when we consider the remainder in between 0 and 6, inclusive of 0, in that case, R will be assuming these values, means starting from 0, 1, 2, 3, 4, 5. 6 cannot be possible here. That is why the remainder can take values starting from 0 up to 5. Now let us check one thing. Means actually a few cases will arise now when we put value of r here starting from 0 up to 5. So for r is equal to 0, a becomes a is equal to 6q plus 0. Yes or no? A is equal to 6q plus 0. Why 0? Because in place of r we have put 0. That is why a is equal to 6q plus 0. That is again equal to 6q because 0 is meaningless here. That is equal to, actually we have to determine whether value of a is even or odd according to value of r. So when we put r is equal to 0 here, we get a is equal to 6q. Now when we factorize this, we can take 2 common here, means 2 can be taken out. Within the bracket 3q will be there. It means what? 2 into something. That means this number can be an even number. Again, when r is equal to 1, a becomes 6q plus 1. So we got that 6q is divisible by 2, but 1 will be left behind, which will be acting as a remainder. That is why 6q plus 1 cannot be an even number. That is why it is an odd number. Now when r is equal to 2, we got a is equal to 6q plus 2. The expression was a is equal to bq plus r. That means a is equal to 6q plus r. So that is why when r is replaced by 2 here, it becomes a is equal to 6q plus 2. So from both these two parts, we can take out 2. Within the bracket, what will be there? 3q plus 1. Since in this expression 2 comes as a factor, therefore this is an even number. So for remainder r is equal to 2, a becomes an even number. So when r is equal to 3, we get here a is equal to 6q plus 3. From this we cannot take out 2. I mean, we do not have 2 as a common factor of both the terms here. That is why this number is an odd number. Again, coming to the next value of the remainder, when r is equal to 4, we get here a is equal to 6q plus r. And we can observe one thing, that from 6q plus r, we can 6q plus r, I mean 6q plus 4, we can take common 2. Within the bracket we get back 3q plus 2. That is why in this expression 2 comes as the common factor, and that is why this number is an even number. And for the last value, I mean for r is equal to 5, actually we had considered values of r from 0 to 5. That is why in this case this is the last value of r. So for r is equal to 5, we are getting a is equal to 6q plus 5. In place of r, we have put 5 here. Again, we can notice one thing, that 6q is a 6q is a multiple of 2. We can get a factor 2 out of it. But 5 is not a multiple of 2. That is why from both these two terms, we cannot take common 2. Therefore, this is an odd number. So whatever we have done till now in this question, it is very clear from this discussion that In the previous slide, we got this as an odd number. I mean this number as an odd number, 6q plus 1, while in this case we got 6q plus 3 as an odd number and 6q plus 5 as another odd number. So it is very clear that 6q plus 1, then 6q plus 3, then 6q plus 5 are odd positive integers for some integer q. Now, in the example questions of this exercise, this type of questions, two questions are available. So these questions, in these two questions also, this format only we shall have to apply for getting the required answer. Now coming to question number 3 of this exercise, what is said here? An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So what is said here? Total 616 members we have in the army contingent. It has to march behind an army band of 32 members in a parade. So these two groups are to march in the same number of columns. That means, what is the number of columns? Means in this group, I mean 32 members in this band, similar number of columns here also we should have. That means the maximum number of columns which can be common to both these two groups, we have to calculate that. I mean for this band of 32 members and for this contingent of 616 members must have common number of columns. In these two cases must have common number of columns. So what is the maximum number of common columns in which they can march? That we have to calculate. In other words, we have to calculate the highest common factor of these two numbers. I mean 32 and 616. So here is the solution. What is said here? Here the total number of members is 616, that is already mentioned in the question, and each army band has 32 members. It is said that this army contingent of 616 members will have to march behind an army band of 32 members. That means these 32 members will be forming certain columns. Same number of columns, this contingent members should also frame. We have to calculate what is the maximum number of columns in which they can march. That means what is the total number of, maximum number of common columns. We have to calculate that. So this is nothing but the HCF of 616 and 32. So we have to apply here Euclid's division algorithm. So of course 616 is greater than 32. That is why we have to divide 616 by 32. 616 divided by 32, 1 jar 32 here. So 6 comes down. 11 minus 2 it will be 9, then 5 minus 3 it is 2. So when it is multiplied by 9, we get here 9 2 ja 18, 1 left, then 9 3 ja 27 plus 1 28. How much is left? Of course it is 8 is left behind. So here in this case we can arrange these terms as dividend is equal to divisor into quotient plus remainder. That is what written here. The 616 equals to 32 into 19 plus 8. Here we get a non-zero remainder. That is why 19 will be taking the 32 will be taking the place of the dividend here. Then again 8, this non-zero remainder will be taking the place of divisor, and as a result when we divide 32 by 8 we get the quotient as 4 and the remainder comes as 0 in this case. So since we got a 0 remainder in this step, the divisor here will be acting as the HCF. Therefore the HCF in this case is 8, which gives us the answer that they can march in 8 columns, and this is the answer of question number 3 here. So in this video we had discussed from question number 1 up to question number 3 of this chapter real number exercise 1.1. In the next video we are going to discuss remaining questions of this exercise, that is question number 4 and question number 5, which is very important from examination point of view. Thank you.